Hi, Chem 100. This is Dr. Ricardo. We're going to do the last section for Chapter 9, which is very short. It's only 3 pages of notes. It is how heat interacts with chemical reactions. So a lot of this is review, so we'll get started. So first of all, chemical reactions fall into 2 different classes. The first class is exothermic chemical reactions, which give off heat. So heat is a product of the chemical reaction. If you run the reaction in a vessel that's insulated, at the end of the time that the reaction is over, the heat from the reaction will make its way or permeate into the vessel, and the products will wind up a lot warmer than the reactants. So in those cases, delta H, which is called the change in enthalpy, so H is enthalpy, so I'll write that down for you, okay? It's a fancy word for the heat of the reaction. So if you go on to general chemistry, that's what H is. So H is enthalpy. So delta H is the change in enthalpy. It's H at the end, or H2 minus H1. That's delta H, okay? So we're gonna, we're always interested in the change in the enthalpy of the chemical reaction, okay? So that delta H is equal to negative, is a downhill reaction. It gives off energy. And another word to say it is it gives off heat or liberates heat. The opposite of that is an endothermic chemical reaction, a reaction that requires heat in order for it to occur. So delta H would be positive and it absorbs heat. Classic example of that is cooking an egg. Cooking an egg is a one-way process. If you crack an egg and you put it on a pan and you don't turn the heat on, the egg is just going to sit there. It's not going to cook on its own. As soon as you provide the outside energy, the energy that's absorbed by the chemical reactions, the egg changes into a cooked egg, which you can't go backwards from. Okay, so here's a couple of examples. Hydrogen plus chlorine, right? Both of those are diatomic, so that's why the 2's react to make 2 molecules of hydrochloric acid. So basically, one H goes with one Cl, another H goes with another Cl. This would be considered a combination reaction. Well, when that happens, this reaction gives off 185 kilojoules of energy for each mole of reaction, just the way it's written. So if you see positive delta H on the on the product side, that means delta H for the reaction is negative. If you give off energy, if energy is a product, delta H is negative. It's downhill. The products are much lower in energy than the reactants. So here's the reactants, the H2 and the chlorine. They are more unstable. Their bonds are weaker than the products, the 2HCl. Those guys are the stronger ones. How much is this downhill process? In this particular case, I went down 185 kilojoules for every mole of reaction that you see. Okay, 185 kilojoules is the height of this. This is a scale of H on here. It's really the potential energy of the reactions, so delta H is the difference of it. Okay? All right, so again, if it's written on the product side, delta H is equal to negative. Opposite of that, nitrogen plus oxygen in the atmosphere requires energy. So usually that energy comes from sunlight. So in the upper atmosphere, the nitrogen does react to small degrees with oxygen plus energy. This actually also happens in the engine of your car. You make a little bit of nitrogen oxide. So this one, the 181, is on the reactant side. That means it needs that amount of energy. You have to put in 181 kilojoules of energy, and so delta H would be positive. So a good multiple choice question would be for me to write it out like this and ask you, what is delta H? And you need to say it's positive 181 versus negative 181. It's just a coincidence that this is 185 and this is 181. Okay, they can be all over the place. They can be 500, 200, 20, depends on the chemical reaction. Okay, so what would this one look like? I'll get a better pen. This one is uphill, So I start out down here, here's my scale of H, start out here, and I wind up 181 higher than I originally started. So this is uphill by 181, and I always have to go over a little mountain to get there, and these are the reactants, nitrogen plus oxygen, these are the products, okay, uphill. So delta H is the difference in H. Uphill is written on the left-hand side of the chemical reaction. Okay? So delta H of reaction is the quantity of heat either produced or absorbed by a chemical reaction. Again, the fancy name for it, I really should write it on here, is the change in enthalpy. Okay, new term. What is this little barrier or hill that I have to overcome? Well, it has a name. It's called the energy of activation. It's the amount of energy that must be supplied to start a chemical reaction. Energy of activation, E-act, is always a positive number. It can never be negative. Okay? Because if it's exothermic or endothermic, you need to get up over the hill. So the definition of the energy of activation is the amount of energy from the starting point to the highest point. So here you are, you're going on a hike. You're going to start your hike over here. You park your car, and you drove up a road, and it puts you at a higher elevation. You've got a short hike up, right? You get to the top of the mountain, you look out, you have a sandwich, you're like, ooh, this is great, what a great hike. And then you want to go finish up, and you finish up much lower in this case. Well, guess what? Somebody from your family comes and picks you up at the end of the hike. So this is a one-way hike, right? And you wind up a lot lower than you started, but you also had to go up over the mountain. So the first part of the hike is very hard, and then you have the nice downhill part over here. Okay. All right, so in this particular case, the chemical reaction is the combustion reaction, which we know will always have a delta H that's negative. They're always exothermic, but it still requires some energy to get it started. So I still have to get up over the hill. So the reaction is methane plus oxygen, gives me carbon dioxide, water, and as a product, 890 kilojoules of energy. I tell you that E-act is equal to 200, and then I ask you to draw this diagram. So first thing, from the 890, the fact that it's written as a product over here means delta H is negative, and this is an exothermic reaction. Therefore, you go downhill by 890. So first thing you would do is draw this line, write the reactants over there, write the products over here, and then from here to here you would sketch in that that's 890. Well, if this is 890, that's basically 900. So 200 should be, about a quarter of the size of it, right? 200, 400, 600, 800. Okay, so between a quarter and a fifth of the size. So try to scale it correctly. Don't make this mountain huge, because according to this, if you get this information and this information, this is 200 compared to a downhill of 800. So energy of activation you could draw in here is the amount of energy from the starting point to the highest point, and that's this guy right here is the energy of activation. See how it's up, always a positive number, where this one, the difference from here to here, turns out to be down. Okay? Okay, so this is what the potential energy diagram would look like for an exothermic reaction where you're given the energy of activation, okay? Combustion. Okay, now, this is 890 kilojoules for the way the reaction is written, so we can actually use that in stoichiometry, and we'll do that right before we finish this section, is we'll calculate how much heat is evolved when a certain number of grams of methane reacts and goes to product. So we can do that because now we've quantified it. That's got nothing to do with getting up and over the hill. It's got to do with the net change. So this is the number you're going to use in those kinds of calculations. Okay, here's an example, classic example of an uphill chemical reaction, the opposite of combustion or respiration, okay, in the body, would be a photosynthetic reaction. So photosynthesis is always uphill. The energy is provided from the sun, right? Man has not been able to figure out how to mimic this very well. I guess why bother, right? Plants do it so well. We just need to work with the plants and use them. So if you have any kind of green plant material, and algae is also able to conduct photosynthesis. the inside the plant material, this particular chemical reaction happens in a series of steps. It's a long process, okay? And you would learn in biology all of those steps. But the net reaction at the end is 6 carbon dioxide molecules plus 6 waters plus the energy that originally came from the sun goes to making some sort of plant material. In this case, we're going to make glucose. Okay, we're going to make sugar, so this might be happening in the fruit. Ultimately winds up in the fruit of the plant. So glucose plus 6 oxygen molecules, right? This is how the oxygen got to the earth. And this guy would be in the gas phase. This one would be in the liquid phase, right, in photosynthesis. It happens at low temperature. Okay, so I start down here. Here's my potential energy diagram. Remember, potential energy is really H, right? I could write H over here, right? And I start out very low because my 2,519 kilojoules, I have to go up to get to my products. They have higher energy, more unstable, more reactive. This is a very reactive molecule. You have to be very careful in hospitals with tanks of oxygen because they explode, right? They could explode in the presence of anything that's flammable because they support combustion. And here's something that's combustible. These are very safe, downhill, low, stable molecules that don't react. Water and carbon dioxide. That's why they're low on the scale. You go uphill. Okay. Well, how much is this mountain that I have to climb? Well, they told me E-act is 5,000, so it's almost double. So I have to get up over this 5,019 kilojoule mountain. Then I come halfway back down, right? This is 2,500. So you should be able to draw this diagram from this information. Key, the fact that the 2519 is written on the reactant side means that it's delta H is positive, and we call that endothermic uphill. This guy has to be positive. So this is what photosynthesis looks like. Okay? This is what combustion looks like. In photosynthesis, energy of activation is always more than delta H. In combustion, it can be more or less, you don't know, depending on how much this barrier is. Okay, last thing you can realize is you can go backwards. Right? The reaction of glucose plus water is a combustion reaction. So if I went backwards, this guy's energy of activation would be the amount of energy to get over the hill to go backwards. So it would be the difference between these two. It would be 5,019 minus 2,519, which would be exactly 2,500. So going backwards, the energy of activation, which is defined as the amount of energy from the starting point to the highest point, would be plus 2,500. And last piece, how much would delta H be going backwards? Well, that's just the same exact number, only with a minus sign. Because going forward, I go uphill, so it's positive, endothermic. Going backwards, I go downhill, exothermic. So delta H for the backwards reaction would be minus 2,519, and energy of activation for the backwards reaction would be from this point up to the top of the mountain. So how would I get that? Is take this minus this, which would give me positive 2,500 would be energy of activation for the back reaction. Okay, that being said, let's do one calculation to quantify energy in a chemical reaction. So the reaction that we're going to look at is, we'll go back to our methane reaction right here, and I'll give you a very simple stoichiometry question to do with it. Okay? So we have methane. So I give you the balanced reaction. Reacts. This is happening every time on your stove when you're cooking inside your house, to make carbon dioxide and 2 water molecules plus 890 kJ per mole, okay, of energy, and that's energy released. So I know, because this is on a product side, delta H for this is going to be minus that number. Okay. Now, since this is a product, I can look at it and relate it through the stoichiometry. So for every one of these, I create one of those, right? It doesn't have a coefficient. So for each mole of methane that reacts, it's going to give off 890 kilojoules of energy. So here's the question that I'll give you. We'll move this up a little bit. Let me get these out of here. Okay, so here's the question. How much energy is released when methane gas reacts with excess Okay, so if that's the case, we start with 50 grams over here. That's what's going in. And we want to see this guy, energy, coming out. And we want to get that. And what units do we want to get it in? We want to get it in kilojoules, how much energy is given off. So this is our map. This guy's in excess. So it doesn't matter, okay, how much you have. So this is like doing it in an open flame where the oxygen comes out of the air, right? You're not controlling the amount of oxygen. So just like your kitchen stove. So 50 grams go in, how much heat do you get out? And that heat is used for cooking. Okay, so first step, we can never do any stoichiometry in grams. We need to go to moles. So I start out with my 50 grams of methane, right? Substance to the correct number of significant figures that they gave you, unit, and what is it is. So the value, unit, substance. Okay, times. How do I convert to moles? Well, I know my 1 mole of methane goes in the numerator and the molar mass goes in the denominator. We've done this one a lot. This guy is 12 plus 4 is equal to 16 grams per mole. So that comes right from the periodic table, right? Okay, next, this is kind of cool. For every 1 mole of methane that goes in, 890 kilojoules of energy comes out. So 1 mole, so I'm doing the stoichiometry relating this coefficient to this one, okay? If this would have been a 2, then I would have to do it for 2 moles, okay? So whatever is here, that's going to go in the denominator here. So this is for each 1 mole of methane. I'm using it as a conversion factor. One of these, 1 mole of this, is related to 890. You don't have to worry about signs, okay? Kilojoules, okay? So 50 divided by 16 times 890, which makes sense. So the 50 divided by 16 gives you the number of moles. This is written straight across, so if every mole gives you 890, let's see how many moles this is. Okay, so this is just a little bit more, well, let's see, than 3. 50 divided by 16, 3.125. So this is 3.125, so 3.125 if I would get off over here, moles, methane, times 890 will give me how many kilojoules for 50 grams for that amount, right? So it's going to be this number times that number. So you could have just went straight across 50 divided by 16, take that answer, times 890. So times 890. Okay, so you get a lot. So this answer comes out to 2,781 kilojoules of energy is released every time 50 grams reacts. So this is an example of using the delta H that's given in the question and using it in stoichiometry to figure out how much energy is released. Now when you're cooking, you're not interested in the carbon dioxide and the water. You're interested in getting this heat out so you can cook with it. Okay? All right, that's it for this video. Thanks, guys. We'll see you next time in Chapter 10.